kind of the same trajectory that we took when we were working with radical expressions. We first did a lot of simplifying, we did addition, subtraction, and then we started solving equations. This is really similar. And again, it combines everything that we learned here. So we're not really doing anything extra, okay? So we're doing one thing extra, okay? So let's just take a bunch of examples and work through them so that you can see how things change, okay? We're gonna do about 9 examples just to get you accustomed to this, okay? So I'm gonna number them, but before we do this, let's go through an example, and then as we go through, we'll explain how to do it. So let's say that we have x over x minus 2 plus 2 over 3. And we're going to say that this is equal to 2 over x minus 2. And the goal here is to solve for x. Okay. So the first thing that we want to do is we want to find a common denominator. Okay, the reason why we want to find a common denominator is so that we get one fraction on the left and one fraction on the right. Okay, so we're going to combine the fractions on the left and we're going to combine the fractions on the right here, and typically you're only going to see one fraction on each one of the sides. Okay, but the idea is you only want one fraction on the left and you only want one fraction on the right. So you're going to start by combining fractions. In this problem, and in I think every problem that we're going to be doing, you only have to work with one side at the beginning. Okay, to do this, you need a common denominator. And the biggest difference is you want a common denominator for all fractions, not just the fractions on one side. And you'll see why in a couple of steps that come after this. So this means you need a common denominator for every fraction in the equation. Not just the fractions on one side. So let's see what this means. This means we're looking at 3 fractions simultaneously. So we only have to worry about combining the 2 fractions that are on the left, but we actually want a common denominator for all 3 of these fractions. So we're going to look here and we're going to say, okay, what do the other denominators have that this one is missing? So we look at this denominator first. This is missing the 3. So we know that we're going to be multiplying by 3 over 3. Let's make sure that we don't have to multiply by anything else. So we look at the last denominator. It has an x minus 2, but this already has it. So we don't need to multiply by anything else. So this one we're going to be multiplying by 3 over 3. Okay, let's look at the second denominator. This denominator has an x minus 2. This one does not, so we know we're going to be multiplying by x minus 2. Okay, this denominator has an x minus 2, and we are already multiplying by that, so we don't have to multiply by twice. We're going to multiply by x minus 2 over x minus 2. And then finally this one. This is an x minus 2, it's already there. This is a 3, it's not there, so we need to multiply by 3 over 3. And now we just do our multiplication. So, what we get is 3x over, for now, leave it as 3 times x minus 2, plus 2x minus 4, don't forget to distribute, over 3 times x minus 2 is equal to 6, over 3 times x minus 2. So notice we have a common denominator for all three, and all three of them we have 3 times x minus 2. So the key here is don't forget to distribute the 2 up here, okay? That has to get distributed. And now we can combine the two fractions. So 3x plus 2x minus 4 gives us 5x minus 4. Okay, so we've kind of seen this before already, because we said in logarithms, when we were solving logarithmic equations, we said if the bases are the same, the arguments are the same. We did the same thing with exponential equations. We said if the bases are the same, the exponents are the same. Well, here, if the denominators are the same, the numerators have to be equal too, okay? If the denominators are equal and the whole thing is equal, okay, the numerators have to be equal. So we could just ignore the denominators and say 5x minus 4 is equal to 6. So if the fractions are equal, and the denominators are equal, actually there is no comma here, the fractions are equal, and the numerators are equal, the denominators are equal. The same thing would be true about numerators, but that's not going to apply because we're finding common denominators. The numerators must be equal. We are not canceling the denominators. We're ignoring them for now, okay? We're ignoring them for now. Symbolically, we're saying if
then you need to check out our list.
P over Q is equal to M over N, and Q is equal to N, then P equals M. So if you like things written in a very brief mathematical way, this is what we're saying. Okay. And now we just have this really nice linear equation to solve. So we're going to add 4 to both sides. Okay, this gives us 5x is equal to 10. We can divide both sides by 5. And we get that x equals 2. Okay, a couple of things. First, this is why we want one fraction on each side, so that we can use this nice little property that if the fractions are equal and the denominators are equal, the numerators must be equal. We can't do that up here, okay? So we wouldn't have been able to do that at this point. That's why we want only one fraction on each side. Then we can use this property. Now the only thing is we're not done yet, because we left out the denominators here, right? We just set the numerators equal to each other. And we have to check for extraneous solutions, just like we did with logarithms. We said, okay, well, we want to make sure that we have something that's going to give us a positive argument, because otherwise we're not in the domain of the function, meaning the function won't be defined. The same thing is true here. We need to make sure that our original equation is defined. So we have to check for extraneous solutions, okay? Meaning if we plug this into the original denominators and we get something that's equal to 0, then this equation would not be defined and it can't be solved, okay? So we have to go through and we have to check for extraneous solutions. So in order to check for our extraneous solutions, we're plugging into every denominator. If we get any denominator that's equal to 0, then it would be undefined and it's an extraneous solution. So this is our last step. I'll put this one in red. So we did this with logarithms, we did it with radicals, and now we have to do it with rational equations too. We want to make sure we don't get 0, because that would make the fraction undefined. There's actually only one, okay? There's the x minus 2, 2 minus 2 is equal to 0, okay? So this is extraneous. It won't work. It's a solution to 5x minus 4 equals 6. It is not a solution to this equation because this would be an undefined fraction and you can't add 2/3 to something that's undefined. And you can't say that something is equal to something that's undefined. Okay, so we essentially have 3 steps here. First, we only want one fraction on each side. We're going to do that by adding or subtracting. Then we want to see if we want to say that the fractions are equal, the denominators are equal, therefore the numerators must be equal. That's why we needed a common denominator for every fraction so that we could say the denominators are equal. And finally, we need to check for these extraneous solutions, because if we have extraneous solutions, then it's a solution to this equation, to our final equation, but not to the original. Okay, let's take some more examples. We're just going to do a whole bunch here. Once you start to feel comfortable, I told you we're going to do... I said we're going to do 9. I'm confirming that we're going to do 9. So once you start to get really comfortable with these, again, I encourage you, stop the tape, do it on your own, and then you'll see how we do it together, okay? So the second one, we have 5 over x squared minus 3x plus 2 minus 1 over x minus 2 is equal to 1 over 3x minus 3. Okay, so one thing that you always want to do, and we said this when we were doing the addition and subtraction, is you want to factor your denominators, because you might find that it's going to be easier to find a common denominator. Okay, so here we see that we have some denominators that are not factored, so let's factor them. So we want to factor the denominators first. And sometimes this will help us find the common denominator. If we're lucky, it'll make some of these fractions even simpler. That's not going to happen here because our numerators are just constants. So it's not going to make anything easier for us here. Okay. So x squared minus 3x plus 2 is factorable. It's x minus 2 times x minus 1. Sometimes what I'll do is, instead of rewriting the whole fraction, I'll just write in tiny letters and numbers what this actually factors to down here. You can do that. It's up to you. I'm doing it this way so that it's easy to follow along. Okay. Then we have x minus 2 is already factored. There's nothing that you can do about that. And then this is equal to, and this 3x minus 3 is factorable. Remember, so certain things to look for. You're looking for, is it quadratic? Because that might be factorable. Is it a difference of squares? A difference of squares is factorable. And then when you have an a, okay, when you have an a or a coefficient in front of your x or your x squared, you want to see, is there something that every term, is there a factor that every term has in common? And there is. It's a 3. And you can see why this is so important here, because this has an x minus 1, but so does this fraction. So our common denominator is not as complicated as it might seem, okay? I will tell you that if you're getting common denominator where your numerator is going to require you to multiply cubics, you missed something. I'm never going to require you to multiply cubics, okay? So let's figure out what we need to multiply by. Let's start with this fraction. We're looking for what the other fractions have that this one doesn't. This one has an x minus 2, but it's already there. This one has an x minus 1, it's already there. But this one also has a 3, which is not there. So this first fraction has to get multiplied by 3 over 3. Then we go to the second one. This one has an x minus 2, already there. It has an x minus 1, it's not there. But there's also a 3 over here. So we have to multiply by both of those. We have to multiply by a 3 over 3 and an x minus 1 over x minus 1. So we could just write it like this. Okay. And then for the last one, this one has an x minus 2. It's not there. So we have to multiply by x minus 2 over x minus 2. And we have an x minus 1. It's there. Okay. So this one times x minus 2 over x minus 2. So sometimes we get these nice little commercial interludes. So I pause it and start it up again to avoid that so that you can hear what I have to say. But okay. So now we just multiply. 3 times 5 is 15. Remember, don't multiply the denominators unless it becomes necessary, and it's rare that it's necessary. Then we have a minus. This, you distribute the 3, it becomes 3x minus 3. And I'm just going to write all of these as 3 times x minus 2 times x minus 1. Remember, it's all multiplication, so it's interchangeable, it's commutative. And then we have equal x minus 2 over 3 times x minus 2 times x minus 1. We found the common denominator. Once you find the common denominator, you cannot try canceling until the very end. Okay? So I'm not going to do this in an extra step because we've done it a few times. This minus has to get distributed. So it becomes a minus 3x plus 3. Okay? So let's write out what we get there. We have 15 plus 3, which gives us an 18, minus 3x over 3 times x minus 2 times x minus 1 is equal to x minus 2 times 3 times x minus 2 times x minus 1. This is the point where we can say, ignore the denominators. Denominators are equal, fractions are equal, so the numerators must be equal.
Searching for music for your next video? Then you need to check out.
So now we have 18 minus 3x is equal to x minus 2. Okay, so we ignored the denominators, and now we're up to the point where we can solve. Okay, so this is a linear equation. We're going to get all of the x's over to one side, all of the numbers over to the other side, the constants. So that means that we're going to add 3x to both sides just to keep the x positive, but it doesn't matter. Add 2 to both sides. The 3x's cancel on the left, the 2's cancel on the right. And we're left with 20 is equal to 4x. We're going to divide both sides by 4. The 4's cancel, and we get that x is equal to 5. But remember, we have to check for these extraneous solutions. So we have to plug it into each denominator. You can do it after it's factored, okay? So these are our denominators after we factor them. We don't have to plug it into x squared minus 3x plus 2. It's factored, it's the same denominator. You do have to plug it into all of them though, okay? So 5 minus 2 is not equal to 0, so we're okay there. 5 minus 1 is not equal to 0, we're okay there. And that's it. Okay, those are the only cases. So x equals 5 is a solution. So let's review what we did. We factored the denominators first. Okay. We found a common denominator second. Remember, this is a common denominator for all fractions. Or really all rational expressions. It's interchangeable. Okay. Then we combined our fractions. So we had 1 on the left. And 1 on the right. Now we can set the numerators equal to each other. Okay, we're ignoring the denominators for the moment. I say for the moment because we have to still use them at the end to check for extraneous solutions. Then we solved for x. And finally, we check to see if the solution is extraneous. And sometimes you might have more than one, okay? We've only had linear equations. We've only had one solution. Sometimes you might have something quadratic, so you might have 2 solutions, okay? I'm not gonna write this out all the time, but this is the general, and the reason why I'm not gonna write this out all the time is because every single problem works the same way, okay? If your denominators are not factor them. Find a common denominator, combine the fractions so you have 1 fraction on the left, 1 fraction on the right. Ignore the denominators and set the numerators equal to each other. Solve, and then check for extraneous solutions. Okay, so you're ignoring the denominators for the moment because at the very end, when you check for extraneous solutions, you're plugging it back in here. Okay, so when you plug it back in, plug it into the factored denominators. Let's take a bunch more. So some of these are going to be more expressions where they need to be factored. Some might be 3 expressions. They're just going to be all different kinds, but remember, regardless of what we're doing, this process is exactly the same, okay? And sometimes you might be able to skip a step, sometimes you won't. So in other words, it might be that you already have common denominators, so you don't need to find a common denominator. Okay, Let's take the next one. Again, at this point, you should be starting to get a little bit more comfortable, and you should be able to think about stopping the tape, but we're doing 9, so you have some time. So let's say that we have x over 5 is equal to x over 2 minus 9. Okay, so this one is kind of nice because we don't have these algebraic expressions in the bottom. Remember, nothing really changes here. Any whole number, I would rewrite as something over 1. And now we're saying, what can we multiply each of these by in order to get a common denominator? So least common multiple of 5, 2, and 1 is 10. Okay, so this is different because we're looking at just numbers, which we'll do sometimes. So the first fraction can be multiplied by 2 over 2. That's what would give us the 10 there. Over here, you're going to multiply by 5 over 5. And in the last one, it's missing both the 2 and the 5, so you multiply by 10 over 10. So that first fraction is going to give us a 2x over 10 equals, notice the equals is now, there's only one expression on the left instead of one expression on the right. So 2x over 10 is equal to 5x over 10 minus 90 over 10. We combine the fractions. I encourage you, a lot of you are going to feel really compelled to skip this step. Do not skip this step. One of the reasons for not skipping this step is to understand that you can't set the numerators equal to each other until you only have one fraction on each side. And right now you have 2 fractions on this side. So you can't say, well, the denominators are equal, so we're just going to set the numerators equal. You can't say that, okay? So you really can't skip this step. So this is 2x over 10 equals 5x minus 90 over 10. Remember, if you start canceling things out, you're undoing what you're doing. You're undoing your common denominator. I'm going to bring this up here just for space purposes. Now we can say the denominators are equal and the fractions are equal, so we could set the numerators equal to each other. Here we can subtract 5x from both sides. This gives us a negative 3x equals negative 90. So here the x is negative, that's perfectly fine. Okay, there's nothing wrong with that. Keeping your x's positive is just a personal preference. Divide both sides by negative 3. And you get that x is equal to 30. Now, none of our denominators had an x in them, so we don't need to even, there's nothing to plug x into, okay? We had a 5, a 2, and a 1. That means that we don't have a denominator of 0. So x equals 30 is it. We know it's not extraneous. Okay. Okay, let's take another one. So let's take y over 3. Minus y over 6 plus y over 2 is equal to 1. So again, we have all numbers in our denominators, all constants, no variables. So the least common multiple of 3, 6, and 2 is 6. So the first fraction would be multiplied by 2 over 2. That's how we would get there, a 6 there. Second fraction doesn't have to be multiplied by anything. Remember, this goes back to like our linear equations when we were saying what's the least common multiple. Over here we have y over 2, so we can multiply by 3 over 3. And this is like a 1 over 1, so we would have to multiply by 6 over 6. So if we actually do the multiplication, we know all of our denominators should be 6. You should always look at it and make sure that that's actually the case. But we have a 2y over 6 minus a y over 6 plus a 3y over 6 is equal to 6 over 6. Okay, and we can just do all of these at once. 2y minus y plus 3y. So we have a y plus 3y or a 4y. So 4y over 6 is equal to 6 over 6. And at this point, we just get y is equal to, 4y is equal to 6. Right, we set our numerators equal to each other. And then we can divide both sides by 4. And that means y is equal to 6 over 4, which is really just y is equal to 3 over 2. Okay. And again, this can't be extraneous because all of our denominators are constants. They're not algebraic, so there's nothing to plug into. Okay, let's take another one. So we have 2 over x plus 5 is equal to 2 over 5 minus x over x plus 5. So again, now we have algebraic expressions, so we need a common denominator. We start with this denominator. We're saying, what do the others have that this one doesn't? This one has a 5. This one does not have a 5, okay? This one has an x plus 5, not a 5, an x plus 5. So we need to multiply by 5 over 5 here. Now we're going to look at this one and do the same thing. What do the other denominators have that this one doesn't? Both of these have x plus 5s. That's it. So that's what we're going to multiply by. And if we look over here, this one is also missing a 5. This denominator has a 5. This one doesn't. So we have to multiply by 5 over 5. So now it's time to just actually write out our new 3 fractions with their common denominators. So our new fractions with their common denominators are 10 over 5 times x plus 5. Remember, you don't have to multiply the bottoms unless it, at some point, maybe it'll become necessary, but so far we haven't seen any place where that's true. Then we have 2x plus 10. Don't forget to distribute that 2. And then minus 5x over 5 times x plus 5. Here we combine our fractions. We don't have to worry about distributing the minus because there's only one term here. So 2x minus 5x is negative 3x. Again, do not skip this step. Okay, for the purpose of room, I'm going to bring this up here. So we're at the point where we have one fraction on the left, one fraction on the right. We can set the numerators equal to each other. So 10 is equal to negative 3x plus 10. We can subtract 10 from both sides. equals negative 3x, and that's okay. You can get a 0. So we're going to divide both sides by negative 3. Sorry about that. 0 disappeared. When we divide both sides by negative 3, we still get 0. So x is equal to 0. You still have to check for extraneous solutions. Okay, you have to check and make sure that you don't have any things that are just x here. And you don't, okay? 0 plus 5 is 5, so we're okay. But you have to show that you checked. Okay, what you're doing is you're saying 0 plus 5 is not equal to 0. That's what we're checking for, okay? It's okay if the top is 0. That's perfectly fine. It's just that the bottom can't be 0 because then the fraction would be undefined. So x equals 0 is a solution. Okay, let's do another one. I wouldn't, even if you're starting to understand it and get it, I wouldn't stop the tape yet. I would still go through each of the different problems because some of them might be a little bit different. Okay. So our sixth one is 6 minus 5 over x squared is equal to 7 over x. Okay, so again, you want to find a common denominator. So here our common denominator is a little bit easier to find, okay? Rewrite your 6 as 6 over 1. I say it's easier to find because we don't have any pluses or minuses. So we're saying, what do the other denominators have that this one doesn't? Well, this has 2 x's. It has an x squared, okay? This one has 1x. It's just an x to the first. This one includes that one. So we only need to multiply by x squared over x squared here. But this second one, again, this one has an x, but this already includes an x. It's already an x times x. And this here, this is an x squared. It's 2 x's, not 1. So we're going to multiply by x over x. And if we rewrite this, what we get is 6x squared over x squared minus 5 over x squared is equal to 7x over x squared. Combine your fractions. 6x squared minus 5 over x squared is equal to 7x over x squared. And then we get this lovely equation. We love it. We can say, okay, let's cancel out the, not cancel, sorry. Let's ignore the denominators, set the numerators equal to each other. We get 6x squared minus 5 is equal to 7x. This is quadratic, so this is why I say keep paying attention, keep the video on, because you'll get different types. So this is quadratic, which means we want to set equal to 0. Okay, and I'm going to bring this up here. Essentially what we're doing is subtracting 7x from both sides. Okay, so what we wind up with is a beautiful quadratic. 6x squared minus 7x minus 5 is equal to 0. And we're going to say, is this factorable? Okay, so we're looking for numbers that multiply to 30 and add to -7. So I'm going to put that in here, just even for my own benefit in terms of doing the problem. multiply to negative 30, and add to negative 7. So that negative 30 came from multiplying the 6 and the negative 5, the A times the C. I don't know why I wrote 70. I didn't mean to write 70. Negative 7. And we do have numbers like that. We have a negative 10 and a positive 3. So this gives us 6x, so it's more work because it's not an easily factorable quadratic. So we have 6x squared minus 10x plus 3x minus 5 is equal to 0. This is a 5. Okay. So we can factor out from the first two terms. We can factor out a 2x, which leaves us with a 3x minus 5. And then from the second one, we can only factor out a plus 1. Notice I keep writing is equal to 0. That's because we're going to be using that. Okay, we're solving for roots here. So that gives us 3x minus 5 times 2x plus 1 equals 0. This is quadratic, so we're setting each factor equal to 0. So this tells us x is equal to 5 over 3. This tells us x is equal to negative 1/2. Okay, neither one of these are extraneous. Okay, so 5 over 3 is not equal to 0, and 5 over 3 squared is not equal to 0. So this is a solution, and negative 1/2 is not equal to 0, and negative 1/2 squared is not equal to 0. So notice we're plugging into the original denominators. Okay, so you still need to check for extraneous solutions. So this one was really nice in terms of finding the common denominator. It wasn't that hard, but then when we got to this point, it became longer. Not harder, but longer, because we had to actually go through and factor it. Okay, so it's quadratic. Okay, next one. Let's do 2 over x minus 1 over x plus 1 is equal to negative 2 over 5 times x plus 5, 5x plus 5. So I'm going to put in an extra step. We have to factor first, because not all of these have been factored. 5x plus 5, we can factor out a 5. So this is an example of where I say, look at all of the denominators and see if any of them can be factored, okay? Because it could make your life easier in terms of finding a common denominator. And in this case it does, because we wind up with 2 over x minus 1 over x plus 1. And this is equal to negative 2 times 5 over x plus 1. So you can see that this denominator has an x plus 1 in it, whereas over here we might not have seen that so clearly. So you want to factor first, okay? So we can go through and we could say, well, what are we going to multiply by? Here, this first denominator, this one has an x plus 1, this one doesn't. This one has a 5, this one doesn't, okay? So we have to multiply by 5 times x plus 1. On top and on bottom. This one has an x, this one doesn't. Okay, so we're gonna have to multiply by an x. This one has a 5, this one doesn't. So this one needs to be multiplied by 5x over 5x. This one has an x, this one doesn't. Okay, so we'll be careful here. This is an x plus 1, it's not an x. This one has an x plus 1, this one already has it. So this one only needs to be multiplied by x over x. Okay, so now we're ready to combine our fractions. So here, 2 times 5 is 10. So I'm going to put this in here as 10 times x plus 1. We can multiply the 2 times the 5. And I want to do that because now we can distribute that 10. Okay? So this becomes 10x plus 10 over 5x times x plus 1 minus 5x, and then we have a 5x times x plus 1 and then we have equals negative 2x over 5x times x plus 1. We combine our numerators. 10x minus 5x is just a 5x. So we have 5x plus 10 over 5x times x plus 1 is equal to negative 2x times 5x times x plus 1. So notice it's the same steps each time. We factor, we find a common denominator, we combine the numerators, okay, so we combined our fractions, then we're setting the numerators equal to each other because the denominators are the same. So we have 5x plus 10 is equal to negative 2x. This is a linear equation. We always prefer linear equations because we don't have to worry about factoring. We can subtract 5x from both sides, which gives us a 10 equals negative 7x. And I'm just going to move this over up here just for space. Divide both sides by negative 7. This negative could go anywhere. It could go in the denominator, the numerator, or just on the outside of the fraction. I'd like to just put it on the outside of the fraction. Okay, or in the numerator. I tend not to put my negatives in the denominator. Again, that's just personal preference because I don't like negative numbers in the denominator if we can help it. We want to just double check, make sure that we don't have extraneous solutions. So we would plug this in. Negative 10 over 7 is not equal to 0. That comes from the first denominator. From the second denominator, negative 10 over 7 plus 1 is not equal to 0. Okay. Negative 10 over 7 is not 1. Okay, so it is not a negative 1. That's how we know. We don't even have to do anything else. And we don't have to plug it into this 5x plus 5 because we're plugging it in after it's factored. Okay? And we can do that. We haven't changed anything yet. So we could plug it in after it's factored. Two more. Again, you should still stay tuned, even if you're starting to get the hang of it, just because sometimes you get something that looks a little bit different. But I think the next two are pretty similar, so you should try them on your own. So the next one is 4 over 2x minus 6 minus 12 over 4x plus 12 is equal to 12 over x squared minus 9. So this is another case where you have to start out by factoring, okay? This makes it look a lot more complicated than it is. Okay, what you're going to find when you factor is that it's much easier to find a common denominator that way when it's factored. It'll also be easier when you check for extraneous solutions. Okay, so let's start by factoring. 2x minus 6, there is a common factor here. You can factor out a 2, and you wind up with 2 times x minus 3. I'm leaving a lot of space because I know that we're going to be looking for common denominators. Here we can factor out a 4, that's a common factor, that's an x plus 3 then. And then here, the x squared minus 9 is a difference of squares. So you're going to see things like this a lot. So we look here and we say, what do the other denominators have that this one doesn't? Well, this has a 4. This only has a 2. So we're missing a 2, right? 2 times 2 is 4, so we're missing a 2. This one has an x plus 3, this one doesn't. So we know that we have to multiply by 2 times x plus 3. This has a 2, but the 2 is already included in the 4, so we don't have to worry about that. This has an x minus 3, this one does not, so we have to multiply by x minus 3 over x minus 3. Okay. And this denominator has an x plus 3, which is already included. It has an x minus 3, which we're already taking care of. Okay. Now that for the last denominator, well, this has an x minus 3, this one has an x minus 3, this one has an x plus 3, this one has an x plus 3, and then we only have to multiply by 4 because, again, the 4 will include this 2, so we don't have to worry about that. So we can multiply by 4 over 4. Okay. And again, just looking at this, you can multiply the numbers first, which really gives you an 8 times x plus 3, okay? Because 4 times 2 is 8, and then you would just distribute the 8. So what we wind up with in that first fraction is 8x plus 24 over 2 times x plus 3, x minus 3. Sorry, not a 2, a 4. 2 times 2 is 4. And then minus, and this one, you have to distribute the 12, so we get a 12x minus 36. And then again, 4 times x plus 3 times x minus 3. And then minus, equals 12 times 4 is 48. 4 times x plus 3 times x minus 3. So this 8x plus 24 comes from, I'm going to put this in blue just so that you see it, comes from distributing the 8, and the 12x minus 36 comes from distributing the 12. Okay. And again, I'm going to put this as one fraction. You can skip this step just because I want to show the distribution of the minus sign. We get 8x plus 24 minus 12x plus 36. This is a step that you could skip, as long as you're really careful and you don't forget to distribute. So here, if we combine like terms, we get a negative 4x plus 60 is equal to 48. And just for the purposes of room, I'm going to bring this up here. Okay. We can ignore the denominators and set the numerators equal to each other. Okay. You can skip this step in the middle here. You cannot skip both steps. Okay. You have to do at least one of them. but you can't skip both, because the idea is that you must show at some point that you have one fraction on the left and one fraction on the right, so that if the fractions are equal to each other, the denominators are equal to each other, then we can set the numerators equal. Okay, and this is a nice one because we just have a linear equation, so we can subtract 60 from both sides. Okay, that gives us negative 4x is equal to negative 12. And if we divide both sides by negative 4, we get x equals 3. And we are going to have to check to see if this is extraneous. And it is extraneous, because when we plug it into here, this 3 minus 3 is 0. So it doesn't matter that 3 plus 3 is... Okay, 3 minus 3 is not. So this is extraneous. Okay, so a lot of the ones that we've had, it hasn't been extraneous, but you can see that there are going to be times when it is. Okay. Let's do one last one. So the last one is going to be 2 over y squared minus 7y plus 12 minus 1 over y squared minus 9 is equal to 4 over y squared minus y minus 12. So just like before, we have to factor first, okay? You see these y squares, this is going to make it really hard to find a common denominator, okay? So you should be familiar enough with factoring that this should not be that big a deal for you. I'm going to try and leave some room because I know that we are doing common denominators. So y squared minus 7y plus 12, we can do y minus 4, y minus 3. Y squared minus 9 is a difference of squares. That's y plus 3, y minus 3. And then y squared minus y minus 12 is y minus 4, y plus 3. Okay, so again, we need a common denominator, so we're asking ourselves, what do the other denominators have that the first one doesn't? This denominator has y plus 3, this one doesn't. It has y minus 3, this one does. This has y minus 4, this one does. This one also has y plus 3, this one doesn't. So we can multiply by y plus 3 over y plus 3, and then it'll look like the others. It'll have what all of the others have. If we look at the middle one, this one has a y minus 4, this one doesn't. This one has a y minus 3, this one it's already included, so we don't have to worry about it. Again, we're missing a y minus 4. The y plus 3, it's already there, so we can just multiply by y minus 4 over y minus 4. And then in this last one, we're missing the y minus 3. The y minus 4 and the y plus 3 from these other denominators are already included. So we're going to multiply by y minus 3 over y minus 3. Okay. And then like every other case, we're multiplying. So we have to distribute. So do not forget to distribute. That's going to be a big mistake that people are going to make. So just be really careful about that. So that leaves us with 2y plus 6. We have a y plus 3, y minus 4, y minus 3. You should always check that your new denominators are all the same. Then we have minus y minus 4. We were multiplying by a 1. And then a y plus 3. Remember, order doesn't matter here because it's all multiplication. And this becomes a 4y minus 12. Y plus 3. Y minus 4. Y minus 3. I'm just switching the order just so that it's really clear that we have the same denominator all the way through. Okay. I'm going to put this in here as an extra step again, but you don't have to. So we have 2y plus 6 minus y plus 4. Y plus 3, y minus 4, y minus 3 is equal to 4y minus 12 over y plus 3, y minus 4, y minus 3. And I'm going to skip a step here, really just to save some room, and it shouldn't be necessary anymore. Okay, so the step that I'm skipping here is this one. This, when we combine it, is y plus 10. Okay, so I'm not writing it as a whole separate fraction. I'm just saying y plus 10 is equal to 4y minus 12. So we're setting the numerators equal to each other because the denominators are equal. And then this is just a linear equation. So we could solve the linear equation. So we subtract y from both sides, add 12 to both sides. That's going to give us 22 equals 3y. You can divide both sides by 3, and you cannot simplify 22 over 3. That's it. So we get that y is equal to 22 over 3. You do have to plug this in, okay? And I will show that to you, but I can tell you also that 22 over 3, none of that, it's not equal to 4, so it's not going to make this 0. It's not equal to 3, so it's not going to make this 0, and it's not equal to negative 3. So this is not extraneous. 22 over 3 minus 4 is not 0, because 22 over 3 is not 4. 22 over 3 minus 3 is not 0. And 22 over 3 plus 3 is not 0. So notice it's always helpful to keep it in factored form. Okay, this did not come out. I'm going to put it up here. We're too close to the bottom of the page. Okay, but all you're doing is you're saying, is it going to make it 0? So if we know that 22 over 3 is not 3, negative 3, or 4, we know it's not 0. Okay, and that's it. That's everything that we do with rational equations. And the next step is actually going to be to go backwards. If you start with an expression, how can you break it up into multiple expressions? And then we're going to do functions, okay, rational functions. So it should be 2 more video lectures, and then we'll be done with rational expressions. Okay, that's it.